We talk about artificial intelligence as a glowing digital brain floating in the cloud. But the cloud is heavy. It is made of concrete, miles of copper wire, and thousands of servers that run white-hot. This chart shows exactly how much power that physical infrastructure actually drains. Training a single large language model consumes between 50 and 100 gigawatt hours of electricity. You are looking at the annual energy consumption of 4,500 average households, burned in a matter of weeks before a single user types a prompt. And training is only the first step. Every ChatGPT response or AI-generated email requires an inference computation, which draws roughly 10 times the electricity of a standard Google search. With billions of queries running daily, the baseline energy demand is scaling vertically. This math is already colliding with reality. In 2024, Microsoft's total carbon emissions rose by 29%. Google's jumped 48% over 4 years. Their publicly stated climate pledges are quietly buckling under the weight of their own server racks. The United States power grid cannot absorb this. PJM Interconnection, managing electricity for 65 million people, currently has 1,200 gigawatts of power generation projects stuck in a backlog, waiting for grid connection. The physical wires and transformers of the public grid are maxed out. The engineers building the future of AI realized the public grid will fail them, so they stopped waiting for governments. They started building stars. Over $7 billion in private investment has flooded into nuclear fusion, led by the tech giants. They are pouring capital into an artificial sun not because they want to save the planet, but because their core product will mathematically cease to exist without a massive private source of 24/7 baseload power. The Pobrick pitch for commercial fusion is perfect. You take isotopes found in ordinary seawater, smash them together under immense pressure, and harvest a limitless supply of zero-carbon energy. This diagram shows the quiet reality behind that pitch. The most viable fusion reactions require an isotope called tritium. The entire global stockpile on Earth right now is measured in kilograms. A single commercial power plant would burn through massive amounts of it relentlessly. Nature doesn't make tritium, and it decays completely in about 12 years. Right now, our only reliable source is a byproduct from aging Canadian heavy water fission reactors, facilities that are actively being decommissioned. The fusion industry knows this. Their planned workaround is to install a breeding blanket of lithium-6 inside the reactor, theoretically allowing the machine to generate its own tritium on the fly as it operates. This schematic illustrates the immediate cost of that workaround. The breeding process releases a barrage of high-energy neutrons. Those particles smash directly into the reactor's structural steel. Over time, this intense bombardment turns the physical walls of the machine into highly radioactive waste that must be safely disposed of. Fusion is an incredible feat of engineering, but it operates inside the hard, unforgiving limits of material physics. It is an industrial meat grinder that produces radioactive byproducts, not a magical, consequence-free perpetual motion machine. The executives writing the checks are highly aware of these engineering bottlenecks. OpenAI CEO Sam Altman and the leadership at Microsoft know that scaling a commercial fusion reactor could take decades. Their data centers need power tomorrow, so they built a fallback plan. While issuing press releases about visionary fusion projects, tech giants are quietly signing multi-billion-dollar contracts to revive old-school nuclear fission plants and deploy fleets of small modular reactors. To make sure these legacy reactors get built fast enough, tech corporations have deployed their lobbying arms to the U.S. Nuclear Regulatory Commission. They are aggressively pushing to fast-track approvals and rewrite safety and licensing frameworks in their favor. When speaking to the public, the narrative is entirely about clean energy transitions and saving the ecosystem. Behind closed doors, the strategy is entirely about securing heavy industrial baseload power at any cost. We are watching a rapid strategic pivot. The corporations that successfully monopolized the digital software layer of our economy are now moving to monopolize the atomic energy layer of the physical world. Building and running this infrastructure requires staggering physical resources. Beyond the energy itself, these companies are cornering the global supply chains for rare earth superconducting tape and locking down municipal water rights to cool their sprawling server farms. Every time human beings unlock a massive new source of energy, a specific pattern repeats. The institutions that control the power source accumulate the wealth, while the physical costs are outsourced to the most vulnerable. The steam revolution drove the modern world, but it filled Manchester skies with soot, breaking the lungs of workers pulled into the coal seams. The petroleum era allowed for globalized trade, but it left permanent scars across entire continents, poisoning local water tables and destabilizing the climate. The first age of nuclear fission promised electricity too cheap to meter. It also gave us permanent exclusion zones and soil remaining toxic for generations. The public relations language surrounding commercial fusion is coded in utopian optimism, but the corporations racing to build it are driven by the exact same profit motives, the exact same growth mandates, and the exact same market pressures as the energy barons of the 19th and 20th centuries. The greatest threat of private fusion isn't the radiation or the resource drain, or whether the physics will actually work in time. It is the centralization of that much power. Because history shows us that whoever owns the sun decides who gets left in the dark.